Hi, I'm Armin Tavante. I'm a postdoc at the University of Illinois. And in this presentation, I'm going to talk about our recent work on Langevin dynamics for importance sampling and reliability analysis. This is joint work with Professor Paolo Gordoni at the University of Illinois and Professor Calvin Jia at Colorado State University. Computing the probability of rare events like the failure of well-designed systems is the main goal of reliability analysis. The first and second order reliability methods are generally efficient in computing the failure probability. However, the geometry of the failure domain may render them infeasible or prone to significant errors. The standard Monte Carlo simulation is flexible in handling failure domains with different geometries. However, it rapidly becomes computationally intractable due to its slow convergence. Importance sampling can improve the convergence rate of Monte Carlo simulation while retaining its mathematical flexibility. However, its performance depends on the choice of the sampling density. In this presentation, we propose a novel importance sampling method by combining ideas from stochastic dynamics and optimization. We build on state-of-the-art sampling methods that use stochastic dynamics to sample from failure domain. Stochastic dynamics help rapidly reach and explore the failure domain. However, sampling can still be slow when the problem involves expensive model evaluations. So we use the governing equations of such sampling methods to develop a parametric importance sampling density through optimizations. The proposed method converts the sampling problem into an optimization problem that can be solved much faster. We show the mathematical connection between the sampling methods and common density approximation methods based on optimization, where the tuning parameters of the sampling method that improve their convergence rate can also help improve the optimization performance and vice versa. We also briefly discussed the geometric interpretation of the tuning parameters and the role in estimating the parametric importance sampling density. The outline of my talk: after an overview of importance sampling, I will talk about Langevin dynamics to sample from the failure domain. That will set the stage for the proposed method to estimate the importance sampling density that I will talk next. And finally, I will conclude this presentation with a numerical example to illustrate some of these concepts and a few remarks. Importance sampling is a popular variance reduction method that aims to improve the convergence rate of the standard Monte Carlo simulation. Its core idea is to define a sampling density that can sample from the failure domain more frequently than in the standard Monte Carlo simulation. The best sampling density is the one that minimizes the variance of the failure probability estimator, hence the name variance reduction. In this method, we define an estimator to value the failure probability and then minimize the variance of the estimator to find the optimal importance sampling density. However, we cannot directly sample from the optimal importance sampling density as it depends on the unknown failure probability. So we can indirectly sample from the optimal importance sampling density by simulating Markov chain that converges to the optimal importance sampling density. A typical class of such simulation methods is based on the Metropolis-Hastings algorithm, which simulates a random walk type Markov chain that eventually reaches and explores the failure domain. However, it needs many samples to converge due to its random walk movements. So the convergence rate can be improved by designing artificial dynamics that govern the movement of samples rather than relying on random walk type behavior. The governing equation of the artificial dynamics can capture the space geometry to rapidly reach and explore the failure domain, and the concept of using these artificial dynamics for general sampling purposes has mainly been explored in the context of Bayesian inference with no application to importance sampling for reliability analysis. So the equation of motion can be formulated for the artificial dynamics based on the desired performance. The behavior of a general dynamical system can be explained using the Langevin equation, and the discretized equation offers a clearer understanding of how the drift and diffusion terms in the equation of motion contribute to the convergence movement. For example, the drift term acts like a gradient vector that determines the direction and step size of the next move from the current position and velocity. Also, the diffusion term acts as an additional momentum that enables escaping local traps based on the underlying space geometry. With the specific conditions on the general equation of motion, convergence to the optimal importance sampling density is guaranteed with this method. By selecting specific values for the parameters d and q in the equation of motion, several state-of-the-art sampling algorithms can be obtained. For example, Hamiltonian and Langevin Monte Carlo are two popular special cases. In the second case, the metric tensor adjusts the next move of samples based on the space curvature. Such sampling algorithms rely on continuous dynamics to accelerate convergence. However, discretizing the continuous dynamics for the sake of numerical implementations significantly reduces the convergence rate and may even change the converging probability density. So to address this issue, we use the artificial dynamics for an optimization problem rather than for sampling purposes. Our goal is to approximate the importance sampling density by a parametric density using the presented equation of motion. We show that the equation of motion converges to the optimal importance sampling density using the Fokker-Planck equation. The Fokker-Planck equation explains the time-dependent probability density of the response process, and the optimal importance sampling density is derived from the steady-state solution of the Fokker-Planck equation. So the idea here is that the parametric density that approximately satisfies the steady-state Fokker-Planck equation also approximates the optimal importance sampling density. We accelerate the reliability analysis by transforming the sampling problem into an optimization problem using the Fokker-Planck equation. The solution to the steady-state Fokker-Planck equation involves minimizing its residual, which can be viewed as an optimization problem to determine the parametric density. The residual of a Fokker-Planck equation is 0 for the exact solution, and we want to make the residual close to 0 for the approximate parametric density. After some depth algebra and substituting the drift term into the residual, we derive the final form of the residual for optimization. We are essentially minimizing a measure of distance between the optimal and approximate importance sampling densities, and rather than choosing an arbitrary distance measure, we derived it from the formulated equation of motion. The formulated optimization problem is related to minimizing the Kullback-Leibler distance between the optimal and approximate importance sampling densities. The KL distance is a common metric to quantify the mismatch between two densities. It is widely used for developing parametric importance sampling densities, and it captures the logarithmic difference between two densities. We show that it is the lower bound of the derived distance measure. The proposed formulation introduces geometrical aspects into the distance measure that are missing in the KL distance. We can think of this, think of our earlier discussion on samplings based on random walk and stochastic dynamics. One considers geometric aspects, the other one overlooks that. The gradient captures the direction of significant changes in this formulation, and the metric tensor can identify principal curvatures and project the error onto principal directions. So advances in the design of D and Q in the equation of motion in the sampling world can result in improved optimization and vice versa. Finally, we develop a solution algorithm for the formulated optimization problem, which involves three main steps. The first one is to define the space of parametric densities to approximate the optimal importance sampling densities. In this presentation, the parametric density resembles the optimal importance sampling density, but the limit state function is replaced by a computationally efficient surrogate. Adjusting the final form of the optimization problem based on the selected parametric density, the optimization problem amounts to estimating unknown parameter theta by minimizing the residual of the Fokker-Planck equation and also minimizing the mismatch between the limit state function and its surrogate. Finally, we estimate the unknown parameters using an adaptive approach, where we use adaptive approach to generate more failure data for estimating unknown parameters. The most recent expression of the parametric importance sampling density is used to generate additional data for the next update, and the shape of the surrogate is adjusted along the way based on geometrical insights from the generated data. To illustrate the proposed importance sampling method, we consider a component reliability problem where the topology of its level sets changes. The component has a method limit state function with independent standard Gaussian random variables. The location of the most likely failure point on the level sets experiences a sudden change as we approach the limit state surface, which is the zero level set. This sudden change can result in a significant error in estimating the failure probability by converging to the wrong design point. In this example, we use a parabolic surrogate to approximate the limit state function. However, more advanced surrogates, like creating a neural network, can be used as well. Using the Kale distance, which does not capture the space geometry, we converge to the wrong design point due to a trap region, and as a result, significantly underestimate the failure probability. The method underestimates the failure probability at the order of 10 to negative 8 with a total of over 7,000 samples or limit state function calls, whereas the Monte Carlo simulation estimates for the same probability failure is in the order of 10 to negative 6 with the coefficient of variation of 0.05. By incorporating the space geometry, the proposed method overcomes the trap region and finds the correct failure probability with a total of a little over 200 samples. In this presentation, we developed a novel importance sampling method combining the advantages of state-of-the-art simulation methods and optimization. We also provided geometrical insight into the tuning parameters of simulation methods and their role in the proposed optimization formulation. The insights from the numerical example suggest that the stochastic simulations for reliability analysis are essentially a global search for design points, so incorporating the relevant geometrical aspects of the problem is the key to guide the search algorithm, either being simulation or optimization, to escape the local traps and find the correct design points. Our future work will focus on enhancing the proposed optimization formulation by developing advanced surrogates tailored specifically for the problem domain. And additionally, we will explore the integration of active learning functions to enhance the selection of training data, ensuring that they gather the most informative samples to improve the parametric importance sampling density. With that, I conclude my presentation, and we'll be happy to take questions through my email, and you can find more videos available at this channel. Thank you.